Since we're all engineers, we're gonna start chapter 2 with bonding force and energy. Like we talked about last time, everything you say, everything you can touch are molecules or atoms bonded by energy. Everything is energy. Nothing, no, I couldn't think about anything that is not energy. Sorry, you got the largest table in this classroom. So everything, light, temperature, and the solid matters, everything is energy. It's crazy, this universe. And we're gonna start from energy, look at what are the energy and the forces between two atoms. So there are two types of forces between atoms. There are attractive force Fa and repulsive forces Fr. And the magnitude between these two forces, attractive force and repulsive force, really depends on how close are two atoms. Depends on the interatomic distance R. And the net force, since we have positive attractive force and repulsive force, the net force just be the sum between them. Just Fn, it's just Fa plus Fr. Now let's look at how the distance between atoms can affect the magnitude of force. If we have our x direction, we have distance r, that is the distance between two atoms. On y direction, we have force. The upper half of y direction is our Fa, which is attractive force. It's called positive. On the negative half of the y direction is our Fr, which is repulsive force. So imagine if the distance between two atoms are infinite far away from each other, and the attraction force between them are very, very small. Let's start from here. And if you move these two atoms close to each other, and those two atoms will experience an increasing of its attraction force. So the attraction force will increase if you decrease the distance between two atoms. But would that force be increasing like infinitely? No. So at one point, this force reaches the highest peak and drops across the x-axis, and it becomes repulsive force. So if you move two atoms too close to each other, and they're going to experience repulsive force instead of attractive force. And it's a very special point, which is the intersection here. That point, the distance, the interatomic distance, 0. That distance is called R. Oh, it has a name. It's called equilibrium spacing. So what is happening at distance when R equals RO? That's where this curve intersects with this x-axis. What is the magnitude of force at that point? 0. So at that point, our net force equals FA plus FR equals 0. That's a special point when the two atoms reaches this equilibrium spacing, there's no force between them. That's net force is 0. And we're going to talk about that, how that is related to the energy between two atoms. One thing to add on this diagram here, if we want to plot what is the net force, and it's going to look like this. The net force this is a net force, my bad. And the attractive force, it's a force that we use the right curve here. That is the FA. And the repulsive force is this one, FR. The black curve here is F and the net force. Okay, let's zoom out a little bit. Let's draw in how the energy looks like between these two atoms. So the energy between two atoms is also depends on the distance between two atoms. R. Now we have energy on the top. We have ER, repulsive energy, and attractive energy. So let's look at that special point. Let's extend this RO. Equilibrium spacing. At that equilibrium spacing, our net force is 0, and the corresponding energy at that point is also minimum. We have minimum energy at that particular point. So the equilibrium spacing, the RO, it's a sweet spot between two atoms. When two atoms have that distance between each other, and they experience a minimum energy to remain that position. And that is important for our chapter 3 crystal structure. That's how different materials have different arrangement in space. That's because matters are lazy. They want to stay in that minimum energy position. So this is where that comes from. Ooh. Okay, and you may have a question. Here we are talking about energy. How come we have this negative minimum energy? Should energy be the minimum at 0? So remember, this is the energy, this is a potential energy we're talking about here. Just like voltage, electric voltage, you can have positive voltage, you can have negative voltage. Voltage is kind of potential energy. It depends on the reference point, right? You can set a positive and negative. So here, it's a potential energy, so it has negative and positive. And energy and the force has this relationship. The net energy between atoms equals integrate distance forces, net force, times dr. The integration of force with respect to the distance between two atoms. It can be written as EA plus ER. EA is attractive energy, and ER, it's the repulsive energy. So on the top here, for the force can be also written as dE. E is energy here, derivative with respect to dr, the distance between atoms. This is how energy and force look like between two atoms. Then what does those bonding energy can tell us? If two atoms share very strong bonding energy, what does that tell you? How would that reflect on its property? Imagine if you have a piece of paper, you can tear it apart easily. But can you tear apart of a metal bar? No. So the energy between the atoms inside of a metal is stronger than the bonding energy between molecules inside of a piece of paper, right? That gives you a sense of mechanical property. If the bonding energy is stronger, which means it has a stronger material is stronger, it's hard to break them apart. And that can also reflect on the melting temperature. If two atoms share a very large bonding energy, the melting temperature is going to be very high. If the bonding force between atoms are small and weak, the melting temperature is going to be very low. So that's if in the future you see a table of melting temperature between different metals, that melting temperature also tells you how strong the bonding is inside of that metal. You can kind of, based on the melting temperature, to guess which metal is stronger, right? So, ready, done? Besides bonding and besides melting temperature, the bonding energy between atoms also affect one thing we just learned in chapter 6, the most important thing from the stress strain diagram. The linear region tells you Young's modulus, stiffness of a material. That also affects modulus of elasticity, or Young's modulus. Let me give you an example. If we have two different types of material, the net force diagram, one material look like this, another material look like this. We have material A and B. Which material has large Young's modulus? You just guess. Based on the diagram, just give a wild guess. One look like that, one look like that. Which one is stronger or stiffer? A. Looks like A has a steeper slope, large slope than B. So the Young's modulus of A is larger than Young's modulus of B. So A has stronger bonding. B, it's weakly bonded. One thing to tell that is from the previous, there's one equation I mentioned here. Oops. I mentioned that? No. FDR. Never mind. Yeah, but that plot tells you the mechanical property of a material. And it all, besides Young's modulus, it also affects how the material is expanding during high temperature. We all know if you're heating up something, the volume will expand, right? If you cool down something, the volume will shrink or contract. So the bonding energy would also affect that. So first, this expanding upon heating and contract upon cooling, it's defined as the coefficient of thermal expansion. That's something, it's a material property. You will learn that from mechanics of materials. And that's called, we use alpha for the thermal expansion. And if a material has a strong bonding, that will lead to a small alpha value. And if you have a weak bonding, it will lead to a large alpha value. So it makes sense. If something is strongly bonded, even you heat it up, and because the bonding is very strong, it's not large enough to create a large space between two atoms. That's why the thermal expansion is going to be small for materials who are strongly bonded. For materials who are weakly bonded, it's easy to heat it up and see a very large volume change. Those are three things the bonding energy will tell us. Melting temperature, Young's modulus, and thermal expansion. They're all related to the mechanical engineering property. Okay, next, we're going to talk about what type of bonding we have between two atoms. So we have three types of primary bonding. The reason is they are called primary bond because they have strong bonding energy. And those three types are ionic bond, covalent bond, and metallic bond. So we're going to talk about each of them in detail later. Since we have primary bond, of course, we have something is called secondary bond. The secondary bond is weak, has weak bonding energy. Okay. Then we're going to talk about those three different types of primary bonding in details. But before we talk about that, let's watch a video together.
Human